So what I'd like to do now is just sort of show you some representative homework problems that are in the assigned homework and things like that, and how some of this stuff with that we did the magnetic field due to loops and wires and loops at the center sort of come together now. So in one of the problems you'll encounter something like this. There's a piece of wire that's bent like this, and there's a current I traveling in it like that, and they would like to know what is the magnetic field right here at this point. That's what the question is asking. You can look at the details yourself in the problem about exactly what the current is and what the radius of the loop is and all that sort of thing. But just keep in mind that we just had that list that we just looked at that tells us some equations for the magnetic field due to lines and wires and circles. We have directions we can get from the right-hand rule. So bringing all that together, what would you get in this case here? Okay. Well, let's start with the loop just for instance here. So this loop here is a half a loop. And so yes, you would be right. The full loop that we just got at the center, or at the center in the plane of it here, was mu naught I over 2r. I think you'll agree with that. So this is the result here that we got. If you're at the very center of a loop that carries current like this, I around the loop, that would be mu naught I over 2r. But we have half of a loop here, so it would be true that the magnetic field, this semicircle, contributes to this point here, is just going to be half of this result here. So you'll put something like a 4 in the bottom. Okay. How about the direction? Well, that's the magnitude. How about the direction? Well, the current's going to keep traveling, around the loop like this. And so if I got my right-hand rule out and imagine my thumb traveling in the direction of this current here, and I brought my fingertips down into the plane of the board like that, I would get a magnetic field that points into the plane like that. That would be the contribution of the magnetic field due to that semicircle in there. So that's one result. But we have these wires here too. So what do they contribute to this point? Well, the answer to what they contribute to the point is nothing. And the reason why that's true is because I can go over here and look at the Biot-Savart law, which has this cross product in it here. So we go back and look at the wire. What do we have? Well, the wire is sort of traveling along this direction x hat here. That would be the x hat in the Biot-Savart law. And the direction to my observation point is along this wire here is sort of the r hat, which would be this other purple vector right here. There's the x and the r hat. And if you look very carefully, x and r hat are parallel. That means the angle between them is 0. And the cross product always gives 0 for parallel vectors like that. So this wire won't contribute. Neither will that one, because the observation point is 180 degrees. So indeed, the answer to this problem here about the magnetic field at the center of this whole system here is just due to the semicircle. The other problem that you'll find looks something like this. It's a long wire that goes around like this, something like that, and they want to know the magnetic field right here at this point here. Slight variation of this here. You can clearly see a loop here, a current loop right here, and certainly the result is going to be something like a mu naught I over 2r for sure. That's what the loop is going to contribute. No halves or quarters involved or anything like that. But also you have a contribution due to this wire here. So you have two magnetic fields that are actually produced at this point, and I don't quite remember the direction of the current. It doesn't matter. We can still work it out. Let's say it's going to go down like this, and I think it looped around like this, and then comes back out like that. So sort of the current comes in like this, loops around, and goes back out again. So what do we have? Well, we have the wire here contributing the magnetic field due to the wire, something like this, into the plane like that. So we can draw an X with a circle on it and say this little magnetic field here is B due to the wire. And then you can put your thumb in the direction of this current that goes around the loop like this, and see your fingertips are again going to point into the center. You draw another little X like that, and this one here, this is going to be B to the loop. So however you figure this out now, you have to sort of go back to the list and invoke some of the results here. The total magnetic field is definitely going to be a superposition of the wire plus the loop. And there's no half or quarter loops or anything like that. So this will be something like a mu naught I over 2 pi d and a mu naught I over 2r. And you can figure out how the parameters in the geometry match up. The last sort of class of problems that you'll see in the homework are some of the ones that look like this. There is a problem that looks like this. There's a wire that comes in like this, and it gets bent into a circle like that, and then goes straight out like that. And the wires sort of have a common point here that they're sort of geometrically based around like this. There's a point right there, and indeed, this is the point they like to know the magnetic field for. And this loop here sort of subtends some angle theta like that. Something like that. Okay? So how would you handle a problem like this? What would the magnetic field be? Well, you have these two wires here, and for the reasons we already discussed, remember the Biot-Savart law says the magnetic field is proportional to the direction the wire is traveling in dotted into the observation point vector. And for both of these wires here, you'll notice that the direction the current's traveling in x-hat up here and up here going away, they both make these angles of either 0 or 180 degrees relative to this observation point here. So these two wires aren't going to contribute any magnetic field to that point at all. What do you do about this little segment right here? Well, you can do a couple things about it. We have the result here for a full loop. That's mu naught I over 2r. If the loop here has some radius r, which you can see it does in the problem here. And I just drew the r here, but that would be sort of the radius of even this segment right here, distance r like that. It sort of sweeps along and makes out the loop like that. So this is for a full loop. So what do you have? Well, we've already seen a problem where, like for a semicircle like this, a semicircle at that point, you just take the full loop result and divide by 2, right? For the semicircle, that's what we did in the other problem. So there'd be a 4 here, mu naught I over 4r for a semicircle. But we have sort of another fraction of a circle. But you are free, yeah, the symmetry works out well enough in problems like this here that it'd be something like mu naught I over 2r, and then you would just sort of scale this up or down depending on the fraction of theta here. So you can sort of have a theta here divided by a 2 pi, I suppose. You know, what am I talking about here? Well, we're just scaling the result to represent a section of a loop now. So what do I mean by that? Well, if we have the full loop where we're going all the way around, this thing sort of subtends 2 pi radians of angular measure. So we'll get a 2 pi over 2 pi, which will just leave, this one may be a 1, and we'll get a mu naught I over 2r. Good result here. If we just go around half a circle, we only subtend pi radians. That'll be a pi over 2 pi, or just a half. That's how we get the half circle. Or if you have a section of a circle that you don't know what it is, but just subtends some angle theta, then the whole result for the full circle will just get scaled down to be whatever fraction of the wire you do have. So I believe that this is going to be your result here. The angle you get, well, excuse me, the direction. Put your thumb in the direction that the current flows in and point down into the page like that. Once again, you'll get a big magnetic field that points into the page. So you can figure out the magnitude and the direction from some considerations like that.